This is Mr. V. Welcome to this video series on linear programming. This is the final video on finding optimum solutions. So here's the question we've got. And before we start, I want to mention that this question is beyond the scope of what you are expected to be able to do. On your exam, you've got C standard questions, B standard questions, and A standard questions. This is harder than anything you'll be expected to do on your exam. So I call this an omega standard because it is beyond the scope of what we do. But given everything you've learned, we should be able to do a question like this. So I want to show you how we go about solving this problem, so that you can see everything that's involved. Okay, here's the question. A computer assembler makes two kinds of computers. The Conrad has 200 megabytes of RAM and a single processor. The Conrad Plus has 600 megabytes of RAM and a dual processor. That means it has two processors. At present, the assembler has only 40 processors and 10,000 megabytes of RAM in stock, and there's a delay in supply of both, so we're not going to get any more anytime soon. The assembler makes $800 profit on the Conrad and $1,200 profit on the Conrad Plus, and already has an order for 4 Conrad Pluses and 6 Conrads. We're going to take all of this information and sort it out into our variables, parameters, and constraints table. And that is really the hardest part of this question. Okay, remember that variables are the quantities that are able to be changed. So they have to have both a number value, and we need to be able to change what value they are. Reading through this question, we have two types of computers, the Conrad and Conrad Plus. So we can change that, but they're not quantities. Then we can't assign a number value to these, so they're not variables. However, I can change the number of Conrads I have and the number of Conrad Pluses I've got. And that certainly is a number value, and we certainly can change that, and it will affect everything else. So my variables here are the number of Conrads, I'm going to call it K, and the number of Conrad Pluses. I'm going to call that one P for plus. Okay, now all of the rest of the information is either a parameter or a constraint. Okay, so we've got these number values of RAM, so they're quantities, but we can't change them. So these are quantities that can't change, and that makes them parameters. Same with the number of processors. We've got these given values already, so they're numbers, but we can't physically change what they are. And same with profit. So we've got three groups of parameters working here. We've got amount of RAM, we've got number of processors, and we've got profit. Three groups of parameters. Okay, the Conrads have 200 megabytes of RAM. The Conrads have a single processor, so they have one processor each. The Conrad Plus has 600 megabytes of RAM. And the Conrad Plus has a dual processor, so that means two processors in one. I'm going to skip over the rest of the information for the moment. The assembler makes $800 profit on the Conrad. So the profit is $800 and $1,200 profit on the Conrad Plus. Okay. So I've used that information, I've used this information. The rest are constraints. At present, the assembler has only 40 processors available. That means we can only use up to 40 processors. So the number of processors we use has to be less than or equal to 40. We also have a limited amount of RAM. We've got 10,000 megabytes of RAM available. So at the end, the amount of RAM, the total amount of RAM we use, has to be less than or equal to $10,000. We're not given a constraint for profit, but we are told a minimum value for the Conrads and Conrad Pluses. We have an order already for 4 Conrad Pluses, so we need to build at least 4. And we have an order for 6 Conrads, so we need to build at least 6 Conrad computers. Okay, reading my question, I'm told that the objective function is going to be for profit. So this one is my objective. So I'm going to ignore that parameter for the moment being. But I do have linear inequalities for the amount of RAM, the number of processors, the number of Conrads, and the number of Conrad Pluses. So I want to write the constraints for each of these 4 constraints. So the first inequality I have is going to be 10,000 has to be more than or equal to 200 megabytes times the number of Conrads plus 600 megabytes times the number of Conrad Pluses. I'm going to leave some space here for the rearrangement. The second linear inequality is going to be 40 has to be bigger than or equal to 1 times the number of Conrads plus 2 times the number of Conrad Pluses. And again, I'll leave some space here for rearrangement. My third constraint is that the number of Conrads, K, has to be greater than or equal to 6. And the fourth constraint I've got is that the number of Conrad Pluses has to be larger than or equal to 4. Okay. I'm going to rearrange both of these, and I'll do them very quickly. If you get stuck, go back to a previous video that shows you the rearrangement. It looks to be simpler to rearrange for K, so that's the rearrangement I'll do. So I'll end up having K. K will be smaller than or equal to negative 3p plus 10,000 divided by 200 equals 50 plus 50. For my second inequality, I'm going to have K has to be larger than or equal to negative 2p plus 40. Good, nice equations, I like those. Okay, I'm going to shuffle to the side now. There are my inequalities. Here is a grid that I've pre-drawn up. And I'm going to graph these two on my graph. I'm going to put K on this axis. I'm going to put P, Conrad pluses, on this axis. Okay. I'm going to graph these using the gradient method, just to be real quick. So I don't have enough colors here. Equation number 1, our intercept is 50, so start at 50, and for every 1 across I go down by 3. For my graphs it would be easier to do in steps of 2, so down 1 across, across 1 down 3, across 1 down 3, that's across 2 in total, down 6 in total. So 1, 2 across, 1, 2, 3, 4, 5, 6 down, 2 across, 6 down, 2 across, 6 down, 2 across, 6 down, 2 across, 6 down, and you can really stop whenever you have enough points. When you've got enough points, rule them up, draw your line. There we are. And we know that K needs to be less than this line, so we're going to shade below the line. That's equation number 1. Equation number 2 has an intercept of 40, so I'm starting at 40, and for every 1 across we go down by 2. So again, I just want to kind of go across a little more, so across 1 down 2, across 1 down 2. That's overall across 2 down 4. So across 2, 1, 2, down 4, 1, 2, 3, 4. Across 2 down 4, across 2 down 4, across 2 down 4, across 2 down 4. And again, you can really stop whenever you have enough points to draw all of your lines. Line them up, rule, and we're shading below this line. And it starts getting very busy here. And that was inequality number 2. Alright, 2 more inequalities. K has to be larger than or equal to 6. So I'm going to find K equals 6, 2, 4, 6. I'm going to draw my line. And we need to be above this line. And we also know that the number of Conrad pluses needs to be more than 4. So 2, 4. And we need to be on this side of the line. Okay. So the region of possible solutions is given to us in this shape in the center here. Going across to this point, then down. This is our region of possible solutions. Our optimum solution is going to be one of the corners. And I'll use Roman numerals to identify each of those points. Oops, that's not an empty sheet of paper. Here we go. Okay. Now I need to come back to my problem here. We still need our objective function. So our objective function is going to be profit equals something. In this case, we've got $800 of profit times the number of Conrads plus $1,200 of profit for each Conrad Plus. I'm just going to copy that equation to my sheet of working here. So profit equals 800 Conrad plus 1,200 Conrad pluses. And for each of these 4 points, I'm going to figure out what profit we've got. So for I, on my graph, I can read off that P is equal to 4, K is equal to 6. So therefore my profit is going to be 800 times K, which is 6, plus 1,200 times P, which is 4. 800 times 6 plus 1,200 times 4 equals, that is 9,600. Okay, point 2 is this point up the top. At that point, P is still 4, but K now changed to be 32. And again, we'll calculate the profit. Profit equals, you can actually see all of that. There we go. 800 times K, which is 32, plus 1,200 times P, which is 4. 800 times 32 plus 1,200 times 4 equals, that's $30,400. Point number 3 is this one in the middle. At that point, P reading down is equal to 10, K is equal to 20. Therefore, profit equals 800 times 20 plus 1,200 times 10. Grab my calculator. 800 times 20 plus 1,200 times 10 equals $28,000. And my last point, point number 4, is down the bottom corner here, where P is equal to 10, 12, 14, 16, halfway is 15, P is 15, and K is equal to 6. And again, I will calculate my profit. 800 times 6 plus 1,200 times 15 equals 800 times 6 plus 1,200 times 15 equals, that is $22,800. Now this is profit. We want profit to be maximized. Therefore, the best solution is to produce, and the one with the best profit was option number 2. It's the largest profit. So the best solution is to produce 4 Conrad pluses and 32 Conrads to make a profit of $30,400. And that is how you answer a omega standard optimum solutions problem.